Today's our topic of concern is confidence interval. This is where the magic starts, in fact. So, statistical methods are classified into two branches. One is descriptive method, another one inferential methods. Descriptive methods concern with description of the data, and inferential method concern with estimation, with the generalization of the data. For example, if we have collected a data of 1,000 patients and out of those 1,000, we found that 900 suffered with COVID-19 or they have experienced the COVID-19. So we will describe, okay, there is 0.90 probability, or we can say 90% it was a proportion that a patient is has experienced the COVID-19 in a specific area. Inferential statistics actually generalize to the entire population. Like in a population, we have millions of people, and this 0.90, this 90% will give us the clue to generalize to the entire population, and we can say there is 90% chance or 90% probability that that a person can encounter corona. But the question will arise, okay, if you are saying 90% patients are suffering with the COVID or they have actually experienced COVID, so how much are you sure? Or how much are you sure? Or you can say that will the next patient or the next labs will also contain the same proportion or not? So the surety is basically observed using the one of the another kind. I mean, inferential statistics divide further into two types. One is estimation, another one is a hypothesis testing. Estimation is concerned with the question that what will be the values for the entire population using the sample. And hypothesis is concerned with if we have the values, will we get the same values in the next labs in the next experiment. So today we are concerned with the confidence interval, which is actually the topic of concern under the estimation type. So statistical inference is basically it is the branch of statistics which actually concern with generalization of sample information to the entire population. That sample information we call them statistics, and it must be obtained from the representative sample data. Like if we have obtained the data from the adult population, we cannot generalize it to the children or to the any other group of the people. So the statistics, the sample measure which obtained from the any representative data, the and we want to generalize it to the population parameter with certain probability, with certain surety that comes in the branch of statistical inference. And we are jumping to one of the concept is that center limit theorem. The center limit theorem in general is said that if the sample size is large enough, the two have to large enough, then the sampling distribution of a statistic. Sampling distribution is the probability distribution of the sample statistics, like mean or the or standard deviation or something like this. So if the sample size is large enough, the sampling distribution of statistics follows normal distribution with mean mu and standard deviation is sigma over n. This standard deviation, which is a drive, which is the drive form. It is not the exactly single quantity, and it is actually derived from the sampling distribution statistics. We call them standard error. So if the sample, again I'm repeating, the sample size, if the sample size is large enough, then the sampling distribution, which is nothing but the probability distribution of statistics, follows the normal distribution with mean mu and a standard deviation sigma over root n. It means that that the mean of the distribution that also follows this kind of normal distribution pattern, which we have observed in our previous video. So we have also discussed this example again, but it will be work for estimating the confidence interval. So like we discussed that if the excess hemoglobin values with mu is equal to 7 and sigma is equal to 2. And suppose hemoglobin value follows a normal distribution, so we can measure the with inference about the distribution of hemoglobin values. So this was about the data variable, but the same concept will be used for the sample mean also. Here we go. Like mu is 7 here. So like we can say the 7 is here. This is the mean mu. If it is for the sample, we can also call it that we have estimated from the sample. Since the estimation is done from the sample, so we call them, this is one of the sample estimate, and this sample estimate is a singular value. It is a single value, and we can say okay, hemoglobin of the sample is 7, so it means the population must have also the 7 hemoglobin. So after that, we actually did some exercises while adding the standard deviation and subtracting the standard deviation. So if we can find out that what will be the hemoglobin values for 68.2% of the data, then what we have to do, we have to add the standard deviation for the one time in the mean, and we have to subtract standard deviation one time from the mean. So we obtain the value of 5 to 9, which means the 68.2% are the surety, are the actually probability that the hemoglobin values lie from 5 to 9. Similarly, if we want to be 95% sure with 95% probable, so for that we have to add 2 times sigma and we have to subtract 2 times sigma. So it will be like 2 times 2 is 2 times 2, this 2 is 4. So 7 plus 4 is 11 and 7 plus minus 4 is 3. So it means that we will be 95% sure that the values of hemoglobin will lie between 3 to 11. Similarly, we can also do an exercise with the 3 sigma, like 3 is for the is fixed and sigma is 2 here. So the hemoglobin values at T sigma is 13 from 1 to 13. It means we are 99% sure that the hemoglobin value in the population will lie between 1 to 13. So we actually worked out with two type of estimation. One estimation was a single, only one, and another estimation we obtained by finding out the range. So this singular observation, we have also one name in statistics, and these ranges have also we have the name in the statistics. If we how we are obtaining these estimate, like for example for 95.4%, what we are doing, we are adding 2 times sigma and we are subtracting 2 times sigma. So this is one of the kind of estimation. And for 99 to be 99% sure, we are adding 3 times sigma and we are subtracting 3 times sigma. And this probability comes from the normal distribution. So the singular estimate which we just discussed, that the value of 7 is, we call them as point estimate. It actually provides a single number in an estimate of the population parameter. Like we did just in our example of the hemoglobin, the 7 value, if we have obtained from from the sample, that is our point estimate. And we did some exercises by finding out the range of the values with certain probability, like 95% sure or 99% sure. Like in 95% surety, we found that the hemoglobin values lie from uh, 6 to 11. Like, yeah, sorry, lie from 5 to 11. So this 5 to 11 is the interval estimate with the probability of 0.954. So basically, the probability of interval estimate is our confidence. Like I will, like if we are taking the previous example, although it is for the variable, but we can take the concept from that. So we can say that the probability that the confidence level I will be 95% confident that the sample means in the population will lie between sample mean hemoglobin in the population will lie between 5 to 11 for 95% of the population. So there is one more statement using the same ideology like previous example. This time we are talking about the sample mean. That if the mean of the systolic blood pressure is 120 millimeter Hg of 50 sample population, with the standard deviation we obtain is equal to 10 millimeter Hg. So we can find out, we can say there is 95% confidence that in the population of 1000 patients each 950 patient will have the mean systolic blood pressure between 100 millimeter to 140. How we obtain this 100 to 140? If you remember, to find out the 95% surety, we multiply this 10 with the 2 and we add it for the in the 120 and we subtract it in the 120, like 120 into 2 times sigma, like 120 plus 2 times sigma, 120 plus 20 and 120 minus 20. So 120 minus 20 is 100 and 120 plus 20 is 140. So we can say the confidence level, in each sample, in a sample of 1000, each 950 patient will have the systolic blood pressure of from 100 to 140 millimeter Hg using these probability and all that thing. And we have the formula for confidence interval, that is x bar plus minus z alpha by 2 sigma over root n. This is the margin of error, or we can say sampling error, and mu is the value which we have to estimate. X bar is the value of the mean we will obtain for the sample. Sigma is the value of standard deviation which we have been given. N is the sample size, and Z alpha by 2 based on the surety level, or we can say the confidence level, like either to be 95% confident or be 99% confident. So here we go. If the sigma is known and n is large, the value can be observed to sample standard deviation. Sigma is unknown. So here we go. So there is an example. Let's suppose the mean weight of a random sample of 25 is 50 kg, and we have to set a 95% confidence interval for mu sigma is equal to 10 kg. So it means that we have given the value of the mean and we know the standard deviation which is 10, and the sample size is 25. Only we have to find out the z alpha by 2 which is also given, like we want to be 95% sure. So in the normal curve you can find out that the x-axis contain the z values and the y-axis contain the probabilities. So be 95% sure. We can see where this arrow falls. This arrow falls at 1.96. So it means the z alpha by 2 at this moment is 1.96 using this concept. So if we are putting the values x bar is equal to 50, z alpha by 2 1.96, sigma is equal to 10 from the question, n is equal to 25 from the question from the sample. So if we solve this quantity, like if we take the root of 5, it will be 5, and 10 divided by 5 is equal to 2, and if we multiply with 1.96, it would be around 3 point something. So this 50 we subtract this 3 point something with the 50, and we add this 3 point something with the 50, so it will be 50 minus this quantity and 50 plus this quantity. So we got the range of the values 46.08 to 53.92 for using this value. So we can say this is our answer. The lower limit of confidence interval is 46.08 and the upper limit of the confidence interval is 53.92. It means the value of confidence interval from the random sample that we have collected, we can expect that the mean weight in the population to lie between 46.08 to 53.92 95% of the time. Or we can say if we obtain a 95,000 sample, so each 95 out of those 1,000 sample, 950 sample will have the mean between 46.08 to 53.92. Let's we have another example. If you can solve by yourself, it will be very good. That a pharmaceutical QC inspector is investigating the amount of syrup to be poured in a 2-liter bottle. The sigma for 2-liter bottle is 0.05, which is a standard deviation, and a random sample 100 bottles showed the mean is equal to 1.99 liters. So what is the 90% confidence interval estimate of the true mean amount in 2-liter bottle? So we have the mean 1.99. Z alpha by 2 this time is 90%, which is given here, the value is given here, and 90% Z value is 1.645. Sigma is equal to 0.05 here, n is 100, a sample. We will put these values in the equation. X bar is equal to 1.99, Z alpha by 2 1.645, which we obtained from here. 0.05 is the standard deviation, which is given in the question. 100 is the sample size, which is also provided in the sample. So if we can take the root of this one, like the root of 100 is 10, and 0.05 over 10 is equal to 0.005, which we multiply by 1.645, it gives us as a quantity. That quantity will be subtracted from the 1.99 and will be added to the 1.99. This will provide the lower range of the confidence interval, and this will provide the upper range of the confidence interval. The lower range of the confidence interval, after solving this, is 1.9802, and after solving this plus quantity, it is 1.998. So we can say the values of the confidence interval from the random sample imply that we expect in each 90 out of 100. Why 90? Because we are taking 90% confidence interval. 90 out of 100 syrup bottles would contain the population mean amount between 1.9 to 1.99 liters. So this is all about the confidence interval. How do we calculate it and what does it mean?